Our next conic section is the hyperbola. And in this section, section 10.2, we'll graph hyperbola centered at the origin and not centered at the origin. We'll locate the foci of the hyperbola, and we'll write the equation of hyperbolas in standard form. So, the definition for hyperbola is very similar to that of the ellipse. It's a set of all points in the plane such that the difference of the distance between two fixed points, and those fixed points are called foci, is constant. Okay, so here's a picture of hyperbola. So at this point P on the hyperbola, if you take this distance d1 and this distance d2, and those are the distance to these two foci, if you take d1 plus d2, you'll get a constant. Okay? All right. Oh, sorry. Difference. So instead of a sum, this should be a difference. So d1 minus d2. And that's the same for any point on the ellipse. So for example, if I took this point here, Q, if I took this distance here and this distance here and subtracted them, d1 minus d2, the longer distance minus the smaller distance, d1 minus d2, I would get the same number. And that's true for any point on the hyperbola. If you were to take the difference between the distances to those 2 points called the foci, you would always get the same number. Okay, so let's talk about some of the vocabulary associated with a hyperbola. All right, so we already talked about the two fixed points being the foci. The center, so this is the center of the hyperbola. The vertices are these points here on the hyperbola. A hyperbola has two axes, a transverse axis and a conjugate axis. So the axes are lines which divide the graph in half. So the one that goes through the vertices, that would be the transverse axis. Okay? And then the one that goes between the parts of the hyperbola, this one here, that would be called the conjugate axis. Okay. The asymptotes. So asymptotes are lines which tell us how wide or how narrow the hyperbola is. So the asymptotes go through the center, and they're the lines which tell us, again, how fat or how skinny the hyperbola is. And when we graph them, these terms will make more sense to you. Okay, so here's another picture. This shows that the hyperbola can have two different orientations. You can have a hyperbola where the wings of the hyperbola, the pieces of the hyperbola, are oriented sideways, horizontally, or you can have a hyperbola where the two parts of the hyperbola are organized vertically. And the foci are always found inside the two wings of the hyperbola. Okay? So they're always located on the transverse axis. So maybe we'll add that up here. The foci are always on the transverse axis, inside the pieces of the hyperbola. All right. So the standard form for the equation of a hyperbola will look very similar to that of an ellipse. X minus h squared over a squared minus y minus k squared over b squared is equal to 1. Or, now remember, subtraction is not commutative. So if we write the second term first, it's not exactly the same as the first version of the standard form. So that's why there are two forms for the hyperbola, but only one form for the ellipse. Addition, is commutative, so the order of the terms doesn't matter. Now you'll notice that the presentation I'm doing differs slightly from the one in your textbook. I've never understood why a lot of textbooks choose to give you two completely different formulas for the hyperbola. It's easiest just to interchange the terms and then approach them in exactly the same way. So the center is at h comma k. The position of the terms tells you how to find the vertices. So when the x term is first, when you go to graph it, you're going to move in the x direction to find the vertices, and so the hyperbola will end up looking like this. If the y term is first, you're going to move in the y direction to find the vertices, and so the orientation of the hyperbola will look like that. So the position of the terms tells you how to find the vertices. The slopes of the asymptotes are plus or minus b over a, the square root of the denominators, and the foci are always located, like we said before, on the transverse axis. And unlike the ellipse, the distance to the foci is the square root of the sum of the denominators. Okay, I know that's a lot to take in, so let's try graphing a hyperbola. So let's graph this hyperbola. The first thing we're going to do is we're going to find the center. And just like before, we're going to start with an easy one. X minus what? 0. Y minus what? 0. So we know the center of this hyperbola is at the origin. So let's introduce some axes, and we know the center is at the origin. After we identify the center, let's find the vertices. Now notice that the x term is first, so in the x direction, we're going to move the square root of 9, or 3 spaces, to find the vertices. So 1, 2, 3, 1, 2, 3. So that tells us that we know the orientation of our hyperbola is going to look like this, but what we don't know is how fat or how skinny the hyperbola is going to be. And so the next thing we're going to do is we're going to graph the slopes of the asymptotes. Okay, remember that's plus or minus b over a. And what is b? B is the square root of the number underneath y. So b is 5. And a is the square root of the number under x, so a would be 3. So the slopes of the asymptotes are plus or minus 5 over 3. So we're going to go up 1, 2, 3, 4, 5 over 1, 2, 3. Up 1, 2, 3, 4, 5 over 1, 2, 3. And now let's go ahead and graph the asymptotes. I'm going to put some more lines to aim for so I can try to graph this a little more accurately. So the asymptote, this has a slope of negative 5/3, and this has a slope of positive 5/3. And now we're ready to graph the hyperbola. So you start at the vertex, and you get very close to the asymptote. You start at the vertex, and you get very close to the asymptote. Sometimes people will make a box inside, so let me show you a box. So if you go out 3 in the x direction, go out 5 in the y direction, and it gives you this box right here. And they use the box to help make the asymptotes, so the diagonals of the box are the asymptotes. Okay? All right, and so why don't we go ahead and find the foci. The distance to the foci would be the square root of, and let's go back to our notes here, the distance to this foci is the square root of the sum of the denominators. So 9 plus 25 is the square root of 34, which is somewhere between 5 and 6. So 1, 2, 3, 4, 5, somewhere between 5 and 6. 1, 2, 3, 4, 5, somewhere between 5 and 6. So if we were to give the coordinates of the points, this point here is negative square root 34, comma 0. And this point here is positive square root 34, comma 0. And that's how you graph a hyperbola in standard form. Let's try to do one more before we have to make another recording. Okay, so let's go ahead and graph this one. Again, we'll start by finding the center. So the center is at the origin, 0, 0. Next, we're going to find the vertices. All right, so let's go ahead and get started here. Center is at 0, 0. For the vertices, we look at the first term, and in the y direction, we're going to move the square root of 9, or 3 units, to find the vertices. 1, 2, 3, 1, 2, 3. So that tells us that we know the orientation of the hyperbola is like this, but we need to know how fat or skinny the hyperbola is. So we're going to look at the slopes of the asymptotes. That's plus or minus b over a. B is always the square root of the number under y, so that would be 3. A is the square root of the number under x, so that's going to be 6. So we have plus or minus 3, 6, or in other words, plus or minus 1/2. Okay, so let's go ahead and write in the asymptotes. So up 3 over 1, 2, 3, 4, 5, 6. Up 3 over 1, 2, 3, 4, 5, 6. If you want to see the box would look like this. And the asymptotes are the diagonals of the box. I should have made that dashed. I don't want you to think that that's part of the hyperbola. It's not. And now we can go ahead and graph in the hyperbola. So it's a very wide hyperbola. Here's one piece, and here's the other piece. If we were asked about the foci, remember the foci occur on the transverse axis. So why don't you find the distance to the foci? Okay? Think about our last example. So you find the distance to the foci. Okay, hopefully you found that there was a square root of 45, because that's equal to the square root of 9 plus 36. The square root of 45 is somewhere between 6 and 7. So 1, 2, 3, 4, 5, 6, 7, somewhere in here. 1, 2, 3, 4, 5, 6, somewhere in here. Go ahead and see if you can find the coordinates of the foci. Okay, so hopefully you wrote that the coordinates of the foci are negative square root of 45, 0. And the other one is positive square root of 45, 0. Oops, that's backwards. Because our x-coordinate should be 0, shouldn't it? So let's try that again. All right, so it's 0, square root of 45, and 0, negative square root of 45, and we probably should also simplify the square root of 45. That's the square root of 9 times 5. So in simplified form, we have these as the coordinates of the foci.